Raspberry Pi has been, I guess, the biggest engineering program we've done. Certainly if you include the RP1 engineering program inside it, it's the biggest engineering program we've done at Raspberry Pi. It's the longest. And when did we start? When did we start this?
Depends when you define start, but RP1 started in 2015.
Yeah. This is an 8-year program.
This is an 8-year program.
And it's a program that kicked off before we shipped. We shipped Raspberry Pi 2, hadn't we?
We had.
At that point.
Yeah.
But it was before we shipped Raspberry Pi 0 even, and definitely before 3.
Right, yes. 3 was in the works,
Yeah.
but yes. So it was a long time ago.
Yeah.
I mean,
And so this has been a long program. It's been an expensive program. I mean, I think I totted it up, and it looked like a $25 million program.
Yeah.
And we've touched pretty much everything on the board, right?
we have. I guess we've got new power management silicon, a new Broadcom main processor silicon. We've got the same Wi-Fi as Pi 4. We have RP1, which is what we call Project Y internally. Why did we do it? Well, we'll get to that, I guess. I guess there's some other interesting Pi 5 things like intrusive reflow. Again, we'll probably talk about that in a minute. But there's been a lot of stuff packed into this. Although it looks quite a lot like a Raspberry Pi 4, I guess, there is an awful lot of new stuff.
It looks a lot like a Raspberry Pi 3 because you've trolled everyone, haven't you?
That's true.
What did you do?
I had to move the I had to move the Ethernet connector back from where we put it on Pi 4. So it had to move on Pi 4 because the Broadcom, the pin out meant that we had to bring the wires across the top, again, the sort of the layout of the board meant this time we had to move it back to the bottom again because we needed space to get the Project Y Southbridge chip and the Ethernet PHY underneath, and that just naturally made it fall back into the standard Raspberry Pi layout.
That we've had since B1, B plus in 2014.
Yeah. So that worked well. That worked quite well. I guess the thing to say about this board is it's super, super tight, right? Everything's been co-designed, so we work with Dialog to design the power management chip, with Broadcom on the Broadcom main SoC. Obviously we designed our own Southbridge for the I/O, and each of those we've co-designed the pin out so that all of the wires come out in the right direction.
And I think you see this when you look at the top of the board. What you see is enormous numbers of tracks going across, whether they are coming from the Broadcom SoC down to the two HDMI connectors, whether they are the PCI Express bus coming across to the PCI Express bus coming across to RP1.
That's it.
There's no wires crossing over each other. There's just these parallel motorways.
You've got a four-lane PCI Express that goes from the 2712 chip to the Southbridge, and that's a big bunch of wires, right? If any of those crossed over, it would kind of explode the board tech.
And what is the board technology?
So the board tech is exactly the same as we use for Pi 4, which is quite impressive, really. It's a six-layer board, and we have what's called HDI, which means you have some laser vias in there. So you have laser vias from the top layer to the second, 1 to 2, and then also mirrored on the bottom. So
do you have buried vias in the middle?
And you have buried vias in the middle.
Okay, so you've got 1 to 2. So you've got 6 layers of PCB, and the connections between layers of the PCB are 1 to 2, 5 to 6, and then 2 to 5. So in the middle of the board, and that's a fairly mild. I think probably when we started Raspberry Pi, that was quite a high tech.
It was high tech when we moved to it.
Yeah.
It's fairly. I think it's quite standard now. Not too expensive, and when we sort of know it quite well, we know the materials that go into it. We know the cost structure of it. But actually, it turns out, if you look at the board, as you say, there's big spaces where there's lots of tracks. The biggest issue you have with these boards is if you have to drill any vias, either ones that go all the way through the board or even the ones just in the middle, they put a big blocker in the way of any other tracks, right? So again, you get a double sort of improvement, or it's a double negative if you end up having to cross tracks over, because it just rapidly becomes impossible because you just have to drill holes all through the board and you just can't route your tracks. So it's that co-design, that full stack design, the fact that we can have control over all of these things, has made it possible to put this tech on that PCB.
And that's because that's kind of probably one of two big themes, right, for the for this product in terms of the top level architecture, right? The idea that if we have a custom power management, we have custom core silicon, 16 nanometer core silicon. We've designed our own I/O controller, RP1. If you have that level of control over all of the silicon in the platform, then it drives cost savings in the hardware, and I think that's probably also mirrored. We'll talk about software in another video, but I think it's also mirrored in software, right? That if we understand all of the components in the system in enough detail, and we have been able to kind of fettle them ahead of time, to do work on them ahead of time, then you can take, I guess, cost out of software. You can take performance inefficiencies out of software and get more done with less processing power. Yeah. So that's kind of one big theme, co-design. I think if you just hold the board in your hands, that really springs out at you, and it springs out in terms of these very neat parallel tracks on the board. I guess the other one is integration, right? Mm-hmm. This idea of eliminating shrapnel.
That's it. Yeah. So each of the big bits of silicon, we've tried to pull any of the extraneous bits and pieces back into those bits of silicon. So for example, in the power management chip, this also has, it's a new feature, but we've integrated it as a real-time clock in there.
It's a much requested feature.
It's a much requested feature. It controls the power button, again, a much requested feature. We've got...
Congratulations. So after 12 years of Raspberry Pi,
we
finally have an RTC and a power button.
And it pulls in some of the other things like HDMI, sort of 5 volt power switching and things like this. So little bits of power switching.
Places where you would have had 5, 10, 15 cent little pieces of silicon out on the board. Yeah. Now those have all been mostly slurped up.
Pulled into the main silicon. Devices. So all these features that we've had and we've known about and we know we want, we try and pull them into the main silicon. It's been a feature of all of the platforms, but I think this is the culmination of all of that plus extra goodies as well.
Because it's kind of had this product has had the longest gestation. It's had 8 years gestation, and that's meant there are a lot of these things that you can't, if you only have, I guess, 2 or 3 years of visibility. It's very hard to hoover these things up into core.
That's right.
Into the core silicon.
And I think having that vision from the beginning of the whole South Bridge, and we'd make that do all the I/O. That's kind of driven the layout of the board all the way through. So we knew when we were talking to Broadcom how the thing was going to lay out, or how we envisioned it, and actually it did turn out to, it all fell into place quite nicely. So we've had, there's that thought was there right from the beginning, which has been, it's good to see it play out and actually work.
Yeah, it looks really cute. Right?
It does look really
cute.
So
there's but it still has more placements than any previous.
It does.
It has more components on the board than
it's,
any other previous
the Broadcom silicon is very fast. It's a big chunky processor. If you look at the power management chip, there's a whole ton of inductors around there. One of the top of the chip, there's
11 inductors.
There's 11 inductors, and there's a quad phase, sort of 18 amp supply for the core.
I've been branding it a 20 amp supply.
Well, yeah, we'll do 20 amps, right?
So what does that mean, quad phase?
So that means that you've got effectively 4 switching controllers that are working in anti-phase. So you can either have one massive great inductor, or you can have 4 smaller ones that switch faster. And the 4 smaller ones that switch faster have some advantages, like it can control the voltage at a finer time.
So the way the switcher works, you've got your 5 volts, and then you have your output. The output
of sort of 0.7 to 1 volt.
Yeah. And then you have an inductor out into the system, and then depending on the voltage that it observes coming out of the system, it has a clock period, and it connects the high voltage to that node for a fraction of that clock period. Now, then with a single phase, you have a single clock period, and suppose I use half that clock period. So what you're saying is quad phase. So you could imagine dual phase, where you have a clock period which is like this, and another clock period which is like this, and then you have 2 of these switches feeding the same node. This is where you actually have 4 which are 90 degrees, which is kind of a quarter out of phase, right?
Yeah, so I guess sort of the way I think about it is, these things are running at per phase 2 megahertz, and they're all interleaved, so your total the total rate that the thing can adapt to any kind of voltage change that it's looking at is much faster.
Yeah. So you're going to get effectively an 8 megahertz.
That's right.
A new opportunity to make a different decision. Because of course you have this processor which can be sat there in idle and then a moment later can suddenly decide to run as hard as it can. That's an enormous that's going to pull enormous amounts of current out. Be able to discover in a 1/8 millionth of a second rather than 1/2 millionth of a second
that you need to do something.
That's going to be useful. Right?
Yeah. So that also means that you need less capacitance on the output, right? So less sort of less buckets of charge that need to sort of compensate for the fact that this big beast of a processor can suddenly pull all the power in nanoseconds.
Yeah. I guess it's an important part of the co-design point, right? That if you try and build systems like Raspberry Pi out of generic merchant silicon, you end up effectively having to put the next biggest thing. If we require 8 rails, so we have the sort of 7 relatively low current rails and the 8th very high current core rail. Maybe somebody won't quite sell you that device, and so you end up having to kind of supersize your power management chip and take extra wasteful cost in that corner of the board. If you can get somebody, as we have with Dialog Renesas, if somebody will design you exactly what you need, then there's that much less fat, and you can get that much more done for your dollar.
That's right. Yeah, and yes, it is kind of exactly what we need, which is great. There's no wasted silicon there doing nothing, which is nice, right? And we've managed to arrange it. We knew it was going to go in the corner of the board, so we spent a long time with Dialog, now Renesas, iterating the sort of layout. So the package thermal simulation, the layout, the die, everything's all been designed to sit on the Raspberry Pi 5. And actually, again, that's another one that's just turned out to be really nice.
It's a beautiful piece of engineering, right?
A lovely bit of engineering, yeah.
Now that also has our PD. That also has the client.
That has, yes. So it's got a inside.
So that's USB PD, USB power distribution, power delivery.
Power delivery. So this is your new modern USB PD, USB-C, which has this thing called USB PD power delivery, which is a serial interface that allows your power supply to talk to your power sink, and the boards can request data from the supply, or they can request different voltages, right? So standard voltages are 5 volts, 9 volts, I think 15 volts. So we have that ability now to talk to PD supplies, which is useful.
Because we have a PD supply.
Because we're now launching a new supply with this product, which is a PD supply. So our PD supply is a bit special because so we need more power into the board, right? So we've got a much more chunky processor that can pull a lot more power when it's really heavily loaded.
And we have an aspiration to be able to deliver more downstream power to USB devices.
Exactly, yeah. And other things plugged in, hats, PCI Express, things like that. Fan. So we wanted more power into the board. Now the problem is, we could, and we sort of left this open for a little while, which is kind of one of the reasons PD ended up in there anyway, is that you could do that by requesting the PD supply give you, say, 9 volts at 3 amps, which is, 27 watts. That's the standard. But then you've got to convert that on the board from, 9 volts down to 5 volts and all the other rails.
And that's cost,
so
and
cost silicon,
switching lost.
And cost you efficiency. So you end up throwing money at the problem and throwing power into the board, you're wasting energy. So actually in the end, after we talked about it for a while, we decided to stick with 5 volts, USB-C. Connectors can support 5 amps. Some of these higher PD modes support like 20 volts at 5 amps to get you 100 watts. So we decided to do 5 volts at 5 amp, which is quite hard and unusual. When I say hard, I mean it's a challenge to get the power supply to do that because it's a low voltage at high current, which is a bit challenging. It's a little bit more of a design challenge than the standard, but not impossible. And we've done it. We've got a nice 5 amp supply now, so that allows us to keep the board kind of as it is. So it takes the cost out. You're not throwing any power away, which is important. And yeah, the supply works fine, right? Yeah. So this PD is now really used to just check that the supply can do 5 volts.
So we interrogate the, and I know we had a lot of there was a lot of internal discussion about this, right? About particularly the how much power we can afford to allocate to downstream USB devices, while still reserving enough power to make sure that the Broadcom, in particular, everything on the board, but particularly the big ARM cores inside the application processor, could execute the worst case their worst case workload. So what we've ended up with, I think, is a world where we go and ask so we kind of probably have two worlds. We have a world where we are powered by a traditional three-ish amp a power supply, and a world where this PD subsystem has detected that we're being powered by the shiny new power supply. And then what do we do differently when we discover that?
So if you have, if you have the full fat supply, if you have the new supply, then you get full performance of everything, and you get extra USB current over Pi 4.
So you get, was it 1.5 amps?
So I think we're at 1.5 minimum now,
okay.
Whereas Pi 4 was, I think, 1.1.
Right.
So you get, I think it's 1.5 and a bit, so sort of about half an amp extra,
right.
which is
another 2.5 watts.
Which is another 2.5 watts, and we know that actually Pi 4 level was quite good. It would run quite a lot of stuff without issue.
So without needing a powered hub downstream.
Without needing a powered hub downstream. So that just adds that extra buffer for slightly more greedy disks, for example.
I mean spinning disks
particularly,
substantial transient consumption.
So that's good. So that's the new world. If you plug in a 5 volt 3 amp supply, what we've decided to do is constrain the downstream USB current by default. So you'll be able to run a mouse and keyboard, simple things, but it won't let you, say, boot from an SSD or a spinning disk by default. And you can override that.
Yeah, so it's about making it default safe, right? This thing comes out of the box.
That's right.
If you plug a mouse and a keyboard into it, you'll be fine. If you want to plug more stuff into it, you'll be fine. Unless I think when we're talking about worst case workload on the ARMs, we're talking about pathological workloads, workloads which are really designed to stress the power supply to its limits.
That's right.
So I think what we're expecting, right, is that for most use cases, you will be able to disable this feature, even
and
with
it'll kind of be fine, yeah. But if you do plug lots of things in, again, we're just trying to get away from having something that's marginal and causes confusion. So hopefully it's clear that, this way round, if you buy the new supply, it's all great, and we're not making those supplies particularly expensive. As with anything.
And if you don't want to buy the new supply, it's also still
It's
great.
also fine, and you just turn off the protection feature, which is a fairly easy thing to do, and everything's fine. But just be aware that if you do load it up, then you may suffer some instability, but in unlikely scenarios, I suppose.
So that's the bottom left of the board. We mentioned RTC. How does that work with respect to batteries?
So we don't ship the board with battery. It's got a little 2-pin connector. We have a little cell on a flying lead,
with a
much
sticky
like you laptops and places have, that you can buy and plug in, and then the RTC will keep time over power outages. I mean, it'll keep time anyway, as long as it's plugged in. even if the board's powered off, as long as it's got 5 volts coming in, it's going to keep time. But if you want it to be, completely separate, keep time over, when it's unplugged, then you need the battery.
And then the power button, how does that work?
We have a power button.
Yeah.
I can't believe it. Works like a power button.
We even have a power button on, we even have a little button on the case. We
do, the case, the case is, we've had a little bit more time than we normally would to iterate some of this stuff, and the power button works really nicely with the case. The LED is right behind the button, so the different kind of coloured light comes out very nicely, and the button presses to press the power button.
So you've got a little bendy bit of plastic which pushes on the switch on the board.
John did a great job of iterating until we got a really nice sort of solution to that. So how does it work? I guess much like a laptop sort of power button, when you first plug the Pi in, it will do what a Pi normally does, which is just power up. If you just power it from the wall. If you press the button, Linux should see that, and it should be able to sort of power down the system. Press it again, it will come back up again. Hold it for 5 seconds, it will hard reset, much like a laptop.
And then press it again to turn on.
And then press it again to turn on. And that's about it. Yeah, I think the only other kind of like special feature we've put into that is if you've got a host machine, you plug that USB-C into the Pi with the power button held down, The Pi will boot into USB boot mode. What that means is the host machine can put, upload firmware into the Pi. So this is if you somehow brick your flash on the board.
This is RPi boot mode.
This is RPi boot mode, like compute modules have. Yeah. This is a way to enable that. You're still using the same button.
Get a lot of value out of that button.
Yeah, we've made it do as much as we can. Because it's kind of hard to squeeze a button on the outside.
Yeah, I think I saw somebody.
There's no space for two buttons.
I think I saw someone suggesting using it as an input for the. I think I saw Tim suggesting also using it as an input device for the debug screen. Look at the HDMI debug screen that comes up at the start as well.
Yes.
Like a 1-bit.
Oh, we could do that.
Input button.
Maybe that will turn up in the firmware. I don't know.
We'll see. Cool. So that's the bottom left of the board. I mean that itself was it's a small fraction of the board area, but it's worth emphasising it was an enormous. It was a piece of engineering work at Renesas, at Dialog Renesas, but also in for you and the other people in the organisation specifying and iterating with them what exactly that should look like. Mm-hmm. And that's been going on since 2020.
2020, yes.
2020, yeah, probably. It's pre-pandemic, right? The kickoff for that.
Yeah, just about.
Just about. So that's that corner. Of the board. The middle of the board, obviously, we have 2712. Mm-hmm. Now that's another generation of the 2700X design that's powered all of the Pis. Yeah. We've got those Cortex A76s in there, which are pretty beefy. They're reasonably. There's something like, the sort of back of an envelope number that I have is that they're something like 50 to 60% faster. Clock for clock. Mm-hmm. And we are going to launch at 2.4 gig versus 1.8 gig. So you can imagine you've got about a 33% uplift from clock speed. You've got north of a 50% uplift from architectural IPC. Yeah. So chunky cores.
It's chunky cores. Well, you've used it. It's very fast. Yeah. I guess sort of 2.5-ish times. I guess on some of the JavaScript.
Right. I mean, I care a lot about the JavaScript benchmarks. I think a lot of people care about JavaScript benchmarks because they are the kind of they are directly relevant to end users, and B, they are hard to forge. It's hard to make it. Some of the simpler benchmarks, Drystone, even things like CoreMark these days, SpecInt, you can build cores which target those benchmarks. You can try and crack the benchmark. It's very hard to crack a JavaScript benchmark without accidentally also making a good core. And so where are we? We're kind of, in my mind, I always think about Jetstream 1, right? That's my sort of my favorite Jetstream 1.1. It's my favorite JavaScript benchmark. And you've got kind of a continuum where you have maybe a Pi 3, 3 plus posting 10 to 15 on that. A Pi 4 posting, a Pi 4 with the 1.8 gig clock posting about 50. And then I think if I sat down in front of Liz's M2 MacBook, it's a $7,000 MacBook, that's scoring about 400. So you've got about a factor of 8 between a Pi 4 and the shiniest thing really the shiniest client platform that exists. We're coming in somewhere in the 130 to 150 range here, which is kind of cool, right?
Pretty good. Yeah.
It's a third of it's 2.5 times what we were shipping before. It's a third of the shiniest thing that you can get. Certainly, I have a 2015 MacBook Air which posts about that kind of performance. So it really is quite a respectable client platform.
Yeah, just using it on the desk with the sort of our beta builds, it's very usable.
Yeah.
Right? You can use it. You sort of I forget what platform I'm using, PC versus Pi now. Yeah. Whereas with Pi 4, you could sort of just about.
And we did a lot of work in the pandemic, right? With Pi 4, Pi 4 did. We got lots of Pi 4s out to kids. We had a huge number of kids here in the UK who were sent home without adequate computing facilities. We got a lot of Pi 4s, and then latterly Pi 400s out to those kids, and they were very usable.
Pi 4 was really good and usable. Yeah. But you can sort of tell
it's the kind of difference between good and no compromises.
You don't even, just don't notice that it's sort of, you're not thinking it's a Raspberry Pi.
Yeah. And I think Bookworm's fed into this as well. That, this is, Bookworm is the launch, Raspberry Pi OS Bookworm is the launch operating system for this platform. That came with its own round of performance improvements that have affected all of the previous platforms as well. So you're kind of bringing together kind of two sets of performance improvements at one moment in time.
Yeah. no, it's going to be, well, it is great, right?
Yeah. So we've got 876s at 2.4 gig. We've got Video Core 7. So we have the great grandchild of our little baby.
Time since we built that.
Yeah, we built Video Core 4 in 2007
to 2009.
Yeah. So this is the distant successor of what we bought and what we built and what we shipped in Pi 1 through Pi 3.
Which is very cool, actually.
It is very cool.
We're getting old, you know.
Yeah. It's still got QPUs in it.
I know.
It's kind of fun. So we got Video Core 7. It's got more processing elements. It runs a lot faster, so it's running up. I forget what the number is. I think it's about 900 megahertz.
Yeah, I think that's where we've ended up now.
Yeah. So it's a pretty speedy platform. It's got 12 QPUs in it, I think. So you've got a bigger, faster GPU. Obviously, that's supporting more display output capability as well, right?
Yeah. So we Broadcom have increased the display pipeline bandwidth effectively. So we can do 2 4K 60 now fairly comfortably.
Yeah, remarkably comfortably.
Remarkably comfortably.
You know, as I plug my laptop into a 4K television, and you can feel it struggle. Where this really doesn't seem to break a sweat when you do that. Yeah.
And I guess coupled to that is now LPDDR4X, which doesn't change the game very much, but it's a sort of a slightly more energy efficient LPDDR4.
We've got about twice the achievable memory bandwidth. So we were shipping LP4 3200, and now we're shipping LP4X 4267. But there are architectural aspects.
Inside the architecture, that's where the difference is really more than the. I mean, the externals got faster, but.
So you've got architectural aspects of the 2711 design, the Pi 4 design, that really cut your 3200 down to about 2000. It's very hard to get faster than about 2000 speed grade. So you've kind of got a doubling there. So you've kind of got a doubling of. You've got a lot of doubling in the platform, actually. You've got a doubling of CPU, a doubling and a bit of CPU performance. You've got a doubling of display output bandwidth. We'll come on to RP1 a little bit, and you've got some doublings downstream of that as well. And underpinning all of that is no use doubling all the stuff around the outside if you don't also double your path to memory. Yeah, double your internal performance and double your path to memory.
But we haven't doubled the power. So
we haven't doubled the power. In fact, I think for typical use cases, it's a rather more. I think we have a few, as you can tell by the fact we've had to make some hard decisions about USB. We have a few edge cases which have higher power consumption. My experience of it is it's a cooler
out of the
platform.
box. It's very similar to the current Pi 4 in terms of thermal.
So the idle performance is about the same. The sort of typical performance, my experience is when you put it under typical load, not under pathological load, but you put it under typical load, it's cooler than a similarly loaded Pi 4.
That's right. Yeah, you've got quite a lot more performance per watt. In fact, we should probably try and quantify that. But it's a very cool platform for the performance you get. And even these things have, because it's a more performant processor, you just have more dynamic range in the system, which makes the engineering more of a challenge, right? We've got this very beefy core supply, and we've done a lot of testing that shows that there's quite a lot of margin in there, even in the worst case. But that's good, right? You don't want, you've got to. We made
People are going to enjoy the overclockability.
That's it. There's overclockability, but also we had to make this decision quite a long way before we had the actual silicon that it was going to be coupled to. It turned out we made some good engineering decisions there as well. So
I think we didn't nickel and dime it. We got it just right.
So again, it's another thing that's worked quite nicely.
Yeah. And I guess the other interesting thing in that platform, PCI Express. For the first time, we have a. Should we talk about we talked about the board being largely a Raspberry Pi. Should we talk a little bit about the 2 or 3 things that have changed in terms of board layout? What's changed with the FPC connectors on top of the board?
All right, so what have we got? So all previous Pis had a display and a camera connector. So this uses the MIPI D-Phi and CSI.
Those were 2 lanes.
And they're 2 lanes, right? So the 2-lane camera, 2-lane display.
And they were nominated, this is the camera.
This is the camera, this is the display, and the controllers behind them,
they were unidirectional controllers.
Unidirectional controllers. So on our RP1, what we've done is we've still got these D-Phi, but they're now 4 lanes, and behind each one is a dual controller. So it can either do camera or it can do display. So rather than the old arrangement, 1 camera, 1 display, each 2 lane, you've now got 2 multifunction ports, 2 multifunction FFC connectors, which are now 0.5 mil pitch, so they're physically smaller but have more pins.
And they're the same pin out that we use on the
compute module boards,
the IO boards, right?
The
So it's actually quite a
boards.
mature.
So it's a
we've used this since 2014. It's a fairly
so
mature
it's the
standard for us.
22-way MIPI port, I guess. We're calling it mini camera, mini display. And so you get 4 lanes, and you get each one.
We're on the hunt for some MIPI devices that
well,
need
they do
4
4 lanes, yes, absolutely. No doubt we'll have some coming in the future. Watch this space. But we each of those can be either a camera or display.
So you can have 2 cameras or 2
displays,
or
one of each.
Yeah, in either one. And those are physically located where the old camera,
where the AV jack used to be. So I think
tell me about the AV jack. This is super sad.
AV jack's gone. Sorry. Our lovely.
Got some pads I can solder to.
Yeah. So there are two holes that you can still get TV out, video, composite video. In fact, there's a new video out, composite video system in RP1, which we designed, which can even do some very, I'm told, some very archaic television.
Are we going to go down the television museum, or are we going to just challenge the first? So it's 425 line, is it? The old, is it 425? Whatever the old standard.
Yeah.
Not quite the John Logie Baird standard, but the original philo fonts were.
Yeah, it's going beyond. It's really going beyond my sort of understanding. But I understand that there is a very old.
The
standard.
pre-PAL,
definitely, yes.
Yeah.
So the engineer who did it had a lot of fun making that.
Yeah. So we're looking forward to seeing the Raspberry Pi desktop on one of those 1950s televisions with the mirror, where the CRT is vertical and there's a mirror on the top of it. That's going to be an achievement.
So you have to work a little bit because you'll have to solder a 2-pin header to get that out. And I guess AV wise, we sort of something had to give to squeeze everything onto the board, and I think that was probably the least kind of used, and sort of quite a high cost for the function, right? As well, there's quite a bit of shrapnel in that, and you need the connector. I think it was a reasonable trade.
So that's down there in the same place as the AV connector, roughly the same area as the old camera connector. What's happened over on the left-hand side of the board then?
Left-hand side. So we talked about the bottom left, middle left. We've got a new flexible FFC connector that does single-lane PCI Express. Mm-hmm. So we did look at sort of trying to see if we could squeeze an M.2 connector or something on the board, but for power and physical space reasons, that wasn't really going to happen. So what we've done is we've got a 16-pin FFC, which carries your single-lane PCI Express and control signals. Which
I think we're rating to Gen 2.
Gen 2.
I think it may do Gen 3, but we're rating it.
I think
it's got a Gen 3 controller behind it.
Yeah, I think the Broadcom Silicon has a Gen 3 controller, but will it be compliant to Gen 3? Maybe not. I think it's been designed for best effort, but
I mean, perhaps it's worth having the kind of brief history of Raspberry Pi I/O controllers, right? All Raspberry Pis have looked like core silicon plus I/O controller, and that's and with some bus between them, and so we had 4.5 generations of product through to 3B plus, where that chip was from Microchip, was one of several chips that we bought from Microchip, and that bus was USB 2, and the thing that came out downstream of that was more USB 2 via a hub and 1000, and then latterly 1000 gigabit, sort of reduced gigabit Ethernet. We then had Pi 4, which pulls Ethernet onto the Ethernet
into the main. It brought 2711.
So you have an external G-Fi, and then the I/O chip is the VLI 805,
which is PCI Express to USB 3.
Yeah. And so this is a very standard thing for us, right?
Yes.
That, you can't always fit all the functionality you want into the core silicon. But this kind of, we've taken to the next level, I guess, in a couple of ways. One, because it's something we've designed ourselves, and two, because we put a lot of functionality. So what's in RP1? What does RP1 do for us?
Yeah, lots of things. So I guess USB 3,
yes,
because that's sort of the most visible, I suppose. So you've got two USB 3. Yes. So it's got quad lane Gen 2 PCI Express to
so that's 16 gigabits of bandwidth.
16 gigabits bandwidth.
2 gigabytes a second.
So you've got two USB 3, 5 gigabit USB 3 controllers So each of your blue ports is on a separate controller, which is, if you've got two discs plugged in, that does make a difference. You've got the MIPI camera and display interfaces that we've talked about before.
And that's about 4 gigabits each. They are 1 gigabit per lane, 4 lanes.
Yes.
So about 4 gigabits each.
Yeah. It's about a gigabit per lane, yes, that's right. Okay, we haven't got anything that uses that just yet, but and then we're going around the board. Yeah, it's got an Ethernet MAC on there, so we use the same PHY from Pi 4, but it's plugged.
54213.
Yeah, it's plugged into the RP1 chip this time, and it does the I/O GPIO.
Well, this is a significant architectural change, right? It's a significant architectural change in that what's happened is a lot of that analog used to be integrated into the core silicon. And the nice thing about this is it's let us go down to, so the core silicon is now 16 nanometers. And you can build that 16 nanometer silicon and focus really largely on the digital elements of the design. So that's got HDMI. So why isn't HDMI on RP1?
Right, I mean, it's just a bandwidth thing, right? HDMI has very large amounts of bandwidth. 4K P60, I don't know, do you know off the top of your head what the bandwidth is for that, but it's a lot.
6 gigabits per lane, 24 gig.
Something, yeah, that sounds about right.
24 gigabits for each port.
Times 2.
Times 2, 48, 6 gigabytes a second. Right, so 3 times as much bandwidth as the total bandwidth that we can ship across to.
Yeah, so that naturally, and you've got the kind of high bandwidth display pipeline stuff behind it as well. So that doesn't make any sense to ship off across another, even quite high bandwidth interface. We've got SD card still sticks to the main processor for booting, and again, just sort of naturally, because it sits on the left of the board, it makes sense to put it there. And DDR memory, again, high bandwidth, needs to be close to the processor.
And then the PCI Express, the user PCI Express port, and then this 4-lane.
And then user PCI Express port straight off the main SoC, and the 4-lane comes out on the sort of the right-hand side as you look at the top of the board, feeds RP1.
Outrageous amount of co-design there.
Yes.
You can just kind of go around the ball map. You can see the shape of a Raspberry Pi. When you look at the ball map for that chip, you can see the shape of a Raspberry Pi in the ball map.
The Pi absolutely drove the ball map, and then we had to figure out how to make the ball map.
The ball map drove the floor plan.
Well, yeah.
And then drove the chip
right.
the chip floor plan.
Chip,
and you go and look at the die and the layout of the individual analog elements on the die, and some of the digital elements on the die is driven by the needs of the top level. That's this co-design. That's why you need 8 years to do this, right? There is that level of co-design in the system. So this is a pretty comprehensive overhaul, putting all the analog out there. It's a pretty comprehensive overhaul, putting the GPIO connector out there as well. Now, so what changes and what stays the same about? Because of course the GPIO connector is really important to a lot of people who use Raspberry Pi.
So I mean the pinout's not changed, and the nominal peripheral functions behind the pins haven't changed, but we do have controllers from different places now because it's not Broadcom's silicon. We've got slightly different.
Can you remind me? We've got PL11 UARTs, so they're the same UARTs.
That's right.
I mean, they're via Raspberry Pi,
from
ARM via Raspberry Pi rather than via.
And I think we've got Synopsys, I2C, and SPI, or
and I2S. I can't now. The SPI is the one I can't remember. Is whether that's Synopsys or is, I think it's Synopsys.
Yeah.
I don't think it's PL22.
I think it's Synopsys
because we use PL22. We use the ARM SPI on RP 2040. But I think we made the other decision. Oh, it's an interesting point about RP1, right? Maybe we'll talk about that in the video a little bit. But RP1, the clue is in the name, right? It's the longest lived, although it's the latest chip product to come out from us. It's actually the one that started first, and so some of these decisions were made long before RP 2040 was a thing. Right?
Yeah, and it's a complicated chip, right? It's got lots of different analog, lots of different clocks. It's RP1C0 because this is effectively the third spin of it, right? We had a couple of engineering.
Had a couple of runs at it.
Had a couple of runs at it. And yeah, I mean, it's actually turned out really well in the end. But again, takes a long time. Right?
So although you have GPIOs on the same pins on the connector, you have alternate function, the same alternate function blocks behind the same pins.
The same mux.
The mux out is the same, but the controls themselves are different. But we don't expect that to be an issue because the majority of people are interacting with this
using
via
libraries.
Via libraries. So they're interacting via an abstraction. So
I
we're
mean, no,
expecting
no doubt there'll probably be some little corner cases and bits and pieces, but
Yeah.
we're really hoping that it's sort of 99.9% not an issue.
There's a little bit of fun around I2S, right? That the I2S blocks we've got are unidirectional. So the old I2S block in 270X is a transceiver. It's a bidirectional block where what we have is now we have two unidirectional blocks, a TX and an RX, muxed onto the same pins. So there's a few little quirks.
There'll be a few little quirks, but the idea is that this decision will live for quite some, for a long time, right?
Yeah,
we won't have to change it again.
I think a lot of the success of Raspberry Pi has been about not introducing pointless compatibility breaks between the continuity of silicon supply, lots of the architectural decisions staying the same from generation to generation. So this is a compatibility break, but it's a minor compatibility break, and it's one compatibility break every 12 years. So expect another one in 2036, 2035, 2036 maybe. The expectation is that this RP1 can live for several generations of Raspberry Pi. Right?
I mean, even if we spin it to change it a bit, which I suppose we may do,
the logical structure will stay.
The logical structure will stay the same. We won't again pointlessly break anything. Right? We'll really try and keep it the same.
But this was your concept from like 2015, 2016. It's effectively a chiplet architecture, right? It's before before chiplets were cool. We were building a chiplet. We just didn't know it was a chiplet then, right?
Pretty much, yeah. We've now someone's come up with a name for it.
Yeah. But this idea of putting the right stuff on the right process node, so it's a 40 nanometer chip. 40 nanometers remains a great process for doing analog on, right?
It's a good process. It has been a bit constrained, but less so now, and it's relatively inexpensive.
And we're very familiar
well understood, and we're very familiar with it, right? So it's worked to our favour for sure. And if it's the first chip you do, you want to do something that you're familiar with. But even despite that, I think it's the right kind of process to put all this stuff on. So.
Should we talk about manufacturing briefly?
Because there's some
big
other
manufacturing, certainly one big manufacturing change. What's that?
That's right. So this has been another thread in the how do we make Pi 5 better? How do we make it cheaper?
How do we make it more reliable?
How do we make it more reliable? So what we have worked internally and with Sony, our CM partner, to do is when you make a Pi 4 or Pi 3 or all the legacy stuff, you have three big processes. You have one side of the board where they pick and place components onto. So what they do is they take the bare board, they silkscreen some solder paste, which is basically little teeny tiny solder balls in flux, onto the pads, and then they use machines to put the components on, and then they bake that in an oven, which melts the solder and all the components stick on it.
That's the bottom side first.
Bottom side first.
Yeah.
That's SMT, surface mount. And then they flip it over and they do the other side in exactly the same way. And then the third process, the third big sort of soldery process, is what they call wave soldering. So none of the through-hole components have been put on at this point.
Selective soldering.
Or selective soldering, yeah. And basically, we have robots that then put the through-hole components.
And we've all seen the pictures of the
armed robots,
cobots there.
The cobots,
human-like robots.
So they are putting the through-hole connectors, so USB connectors, GPO connectors, largely those. And then it goes into a big machine, heats the board up, and it squirts solder onto those pins, which then sort of goes into the holes, and then the board comes out, and that's it. It's kind of done, and then it's tested.
And someone looks at it very carefully.
That's right.
That step, right.
So that step, it's a third step. It thermally cycles the board again, but it's kind of splashing solder up on the bottom, which does increase the defect rate, right? Often we get shorts between the pins, which then need to be hand reworked. So we
generate solder balls as well.
It does generate these little teeny tiny solder balls, which occasionally you will see on the bottom of a Pi. Now they're kind of, Sony have and this is a standard thing, they have a standard for it. If it's a certain size, then it's stuck to the board with solder and it's not going to move, and that all
products do that. All products do this, and the interesting thing about our product, of course, is our product is often not in a case.
Not in a case, so you see it. Yeah. And actually, even the surface mount can generate solder balls. If you get like a little bubble or a sputter, it will spit out a tiny bit of solder. So you can never completely eliminate it. But what we're doing is we're using the pick and place machines in a two process. So you do the the bottom side first, as before, and for the top side, you put all your surface mount components on, and then the machines have been adapted to then put the through-hole components on. So we've both worked to get the right sort of handling for the big components on the same pick-and-place machines we use for the small components. And also, we've worked with the connector manufacturers to adapt the connectors so that they work in a way that you put paste onto the holes at the top, put the component on it, and then when it goes through the oven, that paste melts and sucks down the holes.
And so this is intrusive reflow.
We call it intrusive, well, I mean, it's called intrusive reflow. It's not really a new thing, but it's not a thing that I think is done very commonly with the kind of board that we have. And if you turn over a Pi 5 and look at it, it's really, really nice and clean on the bottom. And you don't have the pins protruding through, they're kind of flat on the board.
And this caused you a bit of trouble, right?
And
I mean, you used to use these pins, some of them, right?
So, it's been quite a long process to get this to work. Don't underestimate how challenging it was to sort of convince ourselves that it was all going to work. So we've done a lot of trials.
And we built a bunch of Pi 4s.
And we built 5,000 Pi 4s with this technology. And that taught us that actually it has its other issues in that when we test the boards, you use sort of sharp pins to probe into the test points and onto some of the pins underneath the board. But with intrusive reflow, those pins have changed shape, and that has caused a little bit of test
excitement.
Excitement is
the
I think basically you still get flux on the pins, but it's well controlled. It's sort of over the top of the pin where the solder's been, but that flux is sort of it's slightly different to what you get from the wave solder. So actually, it can gum up the pins of the tester a bit more. So
it's been some fun there. The other one is the protruding pins also had a mechanical benefit when you're in the field, right?
Yes.
That they're protecting if you imagine you've got all around around two and a bit edges of the board, you've got pins
like
sticking
a millimeter and a bit of pin,
and then you've got SD cards socket over on the other side. Yeah. So you've actually got, if you have a component like a crystal or something on the bottom. Do we have crystals on the bottom of the board anymore? What's left on the bottom of the board?
It's mostly little capacitors.
Yeah. But if you've got components on the bottom of the board, they're kind of somehow protected. They're kind of in this convex. They have kind of a convex shape around them protecting them. If you take away those pins, all of a sudden the caps on the board are resting on the table when you put it down, right?
Yeah, we realised once we had the first prototype, it's like, oh dear,
you
put your Pi 4 on the table and the thing that's taking all the,
as you push connectors into it, it's a bunch of ceramic caps.
Pushing
basically.
all your little ceramic caps, mashing them into the table. Yeah. So we've put a couple of little metal, they're actually designed to be ground test points, but they're little metal hoops, sort of where the pins, in the place where the pins used to be on the USB connectors and Ethernet connector. And again, along with the SD card socket, it kind of holds the board off the deck. Yeah. If you
even if it's uncased, you still,
we encourage people to be very gentle with the boards and put them in cases, right? They're not really designed to be thrown around, but it just helps, right? For a low-cost solution to hopefully reducing people's distress when they smash the thing onto the deck. Don't
don't smash the thing on the deck. Don't put it on it. Put it in a case. Get a Raspberry Pi case. Yeah. So that's the platform, right? I mean, that's a lot of that's how you spend $25 million.
And how many years?
Yeah, $25 million, like an eighth, a sixth of my life, something like that. It's the nice thing about it, right? It's a Raspberry Pi. But it's the first one where we have really been able to intercept every element of the design, knowing that element is going to go into Raspberry Pi. There's no real 270X legacy in there. There's no, pretty much everything in there is changed. Even things like the ISP, and we'll do a separate video on the camera pipeline. But like the ISP, that's entirely developed at Raspberry Pi, pushed into the Broadcom design.
It's kind of the most Raspberry Pi ever, because we've had our hands on everything.
It is very Raspberry Pi, and it probably is. We talked about a compatibility break. It probably is. We are spending our this is the most significant architectural overhaul of the platform in its history. It's moved from kind of a monolithic device to a pair of devices that work together and are decoupled by PCI Express to a chiplet. Let's just use the modern words and call it a chiplet design. It's been enormously good fun to work on, right?
it's really nice to be launching it.
Yeah.
I mean,
Yeah.
you know, I think a lot of us are going to go lie down
Yeah.
for a bit. And
Yeah. And I mean, it's also great that it gives us another chance to talk about what the chip team have been working on,
Yeah.
right?
Oh, yeah.
That, you know, we have a lot of people working at Raspberry Pi on silicon, we probably have more people working on silicon that could be justified, and for a longer period, they can be justified. You know, RP 2040 is an amazing object, but you know, it represents maybe a quarter of the work that the chip team have done since 2015, and the vast majority of the rest of that is in this device, is in RP1. And I'm amazed that nobody asked, I'm going to say it now, I'm amazed nobody asked us what RP1 was.
Yeah.
Because when we did RP2, you know, RP 2040 has RP2 written on the top of it.
Yeah.
RP3A0, the design for that we use on 02 has RP3 written on top of it. And I did sit there, particularly once we did RP3, I did sit there sort of waiting for the inevitable.
Yeah,
So what's
who's gonna
RP1
figure
then?
this one out?
What's
Yeah.
RP1 then?
I think RP3, because it has a Pi 3 gen.
Yeah, each of them has a plausible.
It's kind of confused things, which
Yeah.
is fine.
You know, and
Surprise,
RP2, you know,
yeah.
RP2 does not stand
Surprise,
for
RP1 exists.
That's it.
Yeah,
RP2
we
does
are.
not stand for RP 2040. RP2 is the second chip
So it's
program
really
that
nice to be launching this platform with the first one. Finally, we've got it.
Yeah.
We've got it in
Yeah.
the wild. And,
Yeah. Good
it's
fun.
good.
Excellent. Well, thank you for
Yeah.
that.
Well, thank you.
Yeah. Everyone going to go lie down now.
Yeah, yeah.
Cheers.